Hello, welcome back to Untitled Maths. In this video I'm going to be going through the laws of exponents, or indices, which weren't covered in my last video, including those on negative and fractional indices. My goal with this video is to help you understand how the laws are derived and where they come from, so you're not just left with a list to memorize. Remember to like and share this video, subscribe to the Untitled Maths channel, and leave a comment with any feedback or requests for topics or questions. You can find my last video on the laws of exponents by clicking on the icon in the top right corner of your screen. The first law of this video concerns negative powers. A to the power of minus m is equal to 1 over a to the m, which is also known as the reciprocal of a to the m. For example, if we have 2 to the power of negative 2, that's equal to 1 over 2 squared, which is just equal to 1 over 4. Let's consider the example a to the power of 3 divided by a to the power of 5. This can be rewritten as a times a times a, 3a's, divided by a times a times a times a times a, 5a's. We can cancel the a's at the top with the a's at the bottom, so this cancels out with this. Having cancelled everything at the top, we're left with just a 1, and at the bottom we're left with a multiplied by a. This leaves us with 1 over a squared, since a times a is a squared. Now think back to the second indice law that we covered. A to the m divided by a to the n is equal to a to the m minus n. We can apply this law to the same problem that we have here. Here again we can subtract the powers, 3 minus 5, to be left with a to the power of minus 2. Now we've worked out two separate expressions for the same thing. A to the power of 3 over a to the power of 5 over here is equal to 1 over a squared. And over here, we've worked out that it's equal to a to the power of minus 2. As a result, these two must be equal, and this can prove our rule. A particular case of this rule which crops up often is a to the power of minus 1, and that's equal to 1 over a. Remember that a is the same thing as a to the power of 1, so this follows the same structure as the rule above. When applying this rule to fractions, we can treat the inner fraction as a single term. For example here, when we have a over b, we can write that as 1 over a over b. Once you work out this division, it just comes out as b over a. So to generalize, when you have a fraction raised to the power of minus 1, the answer is just the reciprocal, or the flipped version of that fraction. The sixth law is about raising a fraction to a power in itself. It says that when you have a fraction a over b raised to the power of m, that's equal to a to the m over b to the m. This is another rule which is quite easy to prove once you think about what the exponent actually means. Here, a over b cubed is equal to a over b multiplied by a over b multiplied by a over b. Remember that when we're multiplying fractions, we multiply all the numerators together before multiplying all the denominators together. Therefore, on the numerators, it would be a multiplied by a 3 times, which is a cubed. And the same with the denominator, b times b times b, which is b cubed, which again follows our rule. To work out fractions which are raised to exponents which are less than negative 1, we can combine the two rules that we've learned here. Firstly, it's easiest to remove the negative sign from the exponent by changing the fraction to its reciprocal. So a over b would become b over a cubed. And then we can just expand it, like our rule over here. So this would equal b cubed over a cubed. The next rule states that a raised to the power of 0 is equal to 1. This is one which might seem a bit counterintuitive and a bit weird at first. However, when you look at the different ways you can rearrange powers, it might make a bit of sense. Let's start off with something which should make complete sense. A to the power of m divided by a to the power of m is equal to 1. If you've got the same thing and you divide it by that same thing, they cancel out on both sides and you're left with 1 divided by 1. So that's just equal to 1. Now we again think back to the second rule that we learned. A to the power of m divided by a to the power of n is equal to a to the power of m minus n. Now we can rewrite our fraction over here as a to the power of m minus m, since those are our two exponents on the top and bottom of the fraction. However, m minus m is equal to 0 because you're just taking something away from itself. So this fraction over here is also equal to a to the power of 0. Now looking back, again we've created two expressions for the same thing. And this means that they must be equal. Now we start to deal with fractional exponents. A to the power of 1 over m is equal to that mth root of a. This is again most easily demonstrated through an example, where we've got a to the power of 1/2 multiplied by a to the power of 1/2. Now we think back to our first rule. A to the power of m multiplied by a to the power of n is equal to a to the power of the sum of those two powers. So looking back at this expression here, the result is equal to a to the power of the sum of these two powers, 1/2 plus 1/2, which is just equal to 1. Notice that in multiplying these two terms together, we're just multiplying a to the power of 1/2 by itself. You can rewrite this as a to the 1/2 squared, since to square something is to just multiply it by itself, and this is equal to a to the power of 1, which is just equal to a. Now to get rid of the square on this side, we can just take the square root of both sides of the equation. And now we're left with a to the power of 1/2 is equal to the square root of a. Remember that we usually don't write a 2 next to this root sign, but the square root is really just the second root of a, and this follows our rule. In the same way, you can rewrite any a as a to the power of 1 over m raised to the power of m, since those powers cancel out when you expand. Taking the mth root of both sides, we're left with the mth root of a is equal to a to the power of 1 over m. The final exponent law is about raising a base to an exponent where the numerator isn't 1, where it's its own term. Here we've used n to denote that. And this is equal to the mth root of that base a to the power of n. Note that the power n can be written outside of the root or within the root, since it'll still give the same answer in the end. Look at this example, a to the power of 2/3. We can split the power here by rewriting that as a to the power of 1/3 times 2. Now think back to our third exponent law, where if you have a raised to the power of m and raise all of that to the power of n, you're left with a to the power of m times n. We use that here to rewrite this expression as a to the power of 1/3 squared. Now think back to the last exponent law we covered. If you have a raised to the power of 1 over m, that's the same thing as the mth root of a. So we can use that here to rewrite this expression as the cube root of a squared, which fits perfectly in with our rule. Looking back at this stage over here, we can rewrite this expression as a to the power of 2 all raised to the power of 1/3 here, which is the other way around, but keeping the same value. And then, again using our rule number 8, we can rewrite this as a cube root of a squared, proving that this form of the rule is valid as well. This covers the laws of exponents, and now that you understand where they come from, make sure to learn them very well since they come up really often in exam questions. Remember to subscribe to my channel with the post notifications turned on so you never miss a future upload. Thank you so much for watching.